All right. So last time we finished sort of a quintessential problem of fluid flow in a tube. It's probably the solution that you kind of knew already, even if you maybe haven't derived it. You have seen the formula for flux through a cylindrical tube. Cylindrical tube, if you actually have the tube radius and if you know that the fluid is Newtonian and in laminar flow regime. Today we're actually going to start addressing what happens if you don't have a Newtonian fluid but a different one, in which case our expression for the viscous shear stress tau will differ from the one that we introduced as a generalized Newton law. So let's get going. There will be just a brief review. I posted this this PowerPoint for you on Canvas if you want to download it. So essentially we are working on shell balances, and I will first today introduce what it takes to do non-Newtonian fluids, and then we will actually solve a problem. Today we will probably get to start on the problem, but not necessarily solve it completely. All right, so this is what we have completed so far. Today, this part of the actual presentation is not necessarily following the textbook. However, if you want the chapter in textbook that is addressing non-Newtonian fluids, that's chapter 8. So you can actually look things up there, though I'm actually not following the textbook precisely. So just a quick recap of things that there's in homework. There's some things that are related to cylindrical and spherical coordinate system. So just to remind you, this is something that you should know from your undergraduate, but possibly you need to review the actual formulas, and you need to know where they are in our textbook. So Appendix 6 will, for instance, list all of the things relevant to cylindrical coordinate system. So we will have r, theta, and z coordinates, and they're related to x, y, z coordinates in a manner that is probably familiar to all of you. So z remains the same, x is r cosine theta, and y is r sine theta. And if you want to go back and compute r, theta, and z from x and y, this is how you do it. And then one thing that we will actually use a lot and that you kind of need to especially properly integrate in a cylindrical coordinate system. So one problem that we have when we are integrating in cylindrical coordinate system, we have to do that with respect to r and theta. However, if you actually have an expression, for instance, for force that is in theta direction itself, so force is a vector, for instance, on a ball that has a radial direction, okay? Then that Fr, the force that is in radial direction, actually depends on the location, and it depends on r and theta, okay? Depends on r in particular. So in that sense, you actually have to break down the formulation of force in some coordinate system that is either you will have direct access to this dependence on r and theta, so you can integrate it. And often you can do that by expressing your unit vectors, delta r, delta theta, and delta z, in terms of delta x, delta y, and delta z, which don't change. So you can easily take them out of under the integral and put them outside. Okay? So basically one of the examples in your homework that I will ask you for homework will be actually integrating. If you just go and integrate delta r, okay, over a surface, either cylindrical or, if for instance, let's say that we're in a cylindrical coordinate system, you would have to express it as a function of theta, and then this can get out of the integral, and cosine theta you can integrate. Okay, does that make sense? So it's difficult to integrate something that's changing with respect to r unless you know how it's changing with respect to r and theta. So one way to actually do integration in this coordinate system is to use these formulas to express things in terms of things that don't change as a function of r and theta. Delta x, delta y, delta z, they're unit vectors that don't change with respect to location. Okay? So that's something that needs to be done. And if you want to go back, then you have delta x, delta y, delta z expressed in terms of delta r, delta theta, delta z. Again, delta is basically a notation for unit, either unit vector or unit identity matrix. Okay? So if you look at just the cylindrical coordinate system, this is the element in the coordinate system. So if we were just doing a two-dimensional integration, we have to remember that area of this element is not just dr d theta, it's r dr d theta, partly because the r basically changes on the location. So you have to take that into consideration when you're, for instance, using the coordinate system to integrate over surfaces that are given in cylindrical coordinate system. So this is something, there's parts of the homework that are designed to remind you of these facts that you know from calculus. Okay. Now what we are actually interested in, so cylindrical coordinate system is just a tool that we're using that we need to review. We are actually, when we are looking at flowing tube, we are using cylindrical coordinate system, and our little shell that we are considering is cylindrical. So it goes between r and r plus delta r and z plus delta z. So it's sort of a donut. Okay? And we know that when we derive this z momentum balance over the shell for our combined momentum v, we got the following expression. So minus phi z z evaluated between z and z plus delta z. And same thing here, there was a AR, or area that is orthogonal to r direction. Okay, so it's basically going, if this is my curved r direction, it's orthogonal to it. Okay, so this area is what changes between this location and that location, and that gives me this r here as part of the partial derivative, or the function that I'm taking partial derivative of. And that is, for instance, sign that you're actually in a curved coordinate system that changes with location. In spherical coordinate system, you would have r squared here, because this area depends as r. It changes as r squared, as it's a function of r squared rather than r. Okay, so essentially, as further you go away from the center of the coordinate system, the area of the unit element is changing with as r in cylindrical coordinate system and as r squared in spherical coordinate system. So that is reflected here in these partial differential equations. So this is our general momentum equation. If I had a horizontal tube, such as depicted here, this gravity force would typically be ignored. Okay. Now this particular equation, does it depend on the type of the fluid I'm solving for? No, this is actually the most general. I didn't express combined momentum yet, so I don't know what is the relationship between shear stress and the velocity. It's that relationship that actually defines the fluid. Okay? So basically this is for Newtonian fluid in a tube. This is the relationship between shear stress and velocity. Okay? So I might actually have the same shear stress in two different types of fluids, but the resulting velocity distribution will be very different. Okay, so I might have completely the same situation in terms of pressure difference. I might have the completely same, like the same geometry. It's what will actually, my resulting velocity distribution is going to be different between two different types of fluids based on how do I actually express my shear stress. So shear stress in itself will be the same value, but resulting velocity distribution will be different based on the assumptions that I have on this relationship. Okay? So this is a general form for Newtonian fluid.
That equation on the previous slide is not valid for compressible fluids, right?
It is. Again, so you will just have, well, we would possibly have issues. This force would be expressed differently because there we had rho g part and rho was assumed constant. So it would be some sort of average rho, or it would have to be part of the under the partial differentiation. Okay, so this would be replaced with something a little more, because that's the assumption of constant rho is what we made in expressing this, though that's not explicitly stated here. Okay. So Fg still, as long as you replace Fg with something that is related, that you can, that is valid at a point, it should still work out, but it's going to be rho that depends on the location. All right. So again, you also have to be careful. So the way this is expressed here is in Cartesian coordinate system. So this ijk we refer to as xyz. You have to look up for cylindrical coordinate system, what is this expression. So for instance, divergence of v is not going to be partial vr partial r plus partial v theta plus partial vz partial z. Okay, it's not that straightforward. So divergence has a different form, and there will be some of that 1 over r partial vr partial, because you have to account for the changing geometry. Okay, so some part of there will be the partial of r vr basically in there in part of the expression for divergence. So just make sure you look that up before actually calculating or translating something simply between Cartesian and cylindrical coordinate system. Okay, so for Newtonian fluid, what we solved for, we got this classical parabolic system. So this is my Newtonian fluid in a vertical tube. I have a parabolic velocity profile. My tau was linear, and it changes linearly between the r maximum r and the minimum r. Okay, it's a minimum or a zero value in the middle, and it's in absolute sense the maximum value on the solid wall. Okay, whether it's positive or negative depends on where is the fluid. And that is one, for instance, comment that was relevant to the quiz. If you actually have fluid that is inside the tube, okay, your tau r theta, okay, is, or tau r z in this particular case. I think we had tau r theta in the example on the quiz. But tau r z here is z momentum transferred in positive r direction, so transferred in this direction, okay? Now, if your fluid is actually here and your solid surface is here, so basically your solid surface is in the positive direction from the fluid, and you're wondering what is the stress on that solid surface, then tau r theta times the area is the force, and tau r theta is the stress you're after. However, if your fluid is actually outside, okay, so your fluid itself is in the negative direction, so the solid surface is in the negative direction, r direction, from the fluid itself, and you're wondering what is the stress on the surface, then you will take minus tau r theta. Okay? Because tau r theta, in the way it's defined, it's tied to the coordinate system, and coordinate system doesn't know where fluid is. Okay? So you will just have to take a plus. So there's a change of sign. In absolute sense, you will be correct. Okay, so just taken as an absolute value, you will be correct, but plus or minus sign depends on where is the fluid versus solid surface in the coordinate system. Okay, so that's something to be careful about.
So in another sense, all you're doing is you're changing your references.
Yes. Yeah. So tau r theta as defined is that we said fluid in the lesser r on fluid in the larger r, and if you have a solid surface, you're wondering what is the fluid in lesser r doing on the surface, right? And that's in sync with the definition of tau r theta. If your fluid is actually on the opposite side, you just have to multiply it by minus. Okay. Now, what about non-Newtonian fluids? So for the Newtonian fluid, we had the most simple relationship between the shear stress and velocity gradient. It was a linear relationship with a constant coefficient of proportionality that we called viscosity. Okay, so it's if I have any kind of more complex fluid, that relationship will become more complex. Now, a lot of industrial liquids, or a lot of, so for instance, drilling fluid is an industrial liquid. It's a fluid that is designed to, with density, it's matching the stresses in subsurface. So when I actually have that fluid at certain depth, I'm counting on the drilling fluid to counterbalance stresses at depth. Okay? So I have to have denser fluid, water conduit. Okay? So that's one thing. So I will have additives that are simply weight additives in that fluid. Second thing, it can be actually, it has to be complex and sticky enough to bring out pieces of rock. Okay? And for that, water won't do either. So basically there are certain agents that will actually make it sort of, so to speak, sticky and able to carry things out. So actually I might have behavior that is not just that of water, it's actually somewhere in between water and solid, because it has solids within. So a lot of particulate fluids, well, even your regular river is carrying a lot of sand, and in itself is a particulate fluid. It's just that sand in a regular river immediately settles down. Drilling fluid has additives that prevent that. Okay. So basically that's what makes it more complex. What we call rheology is the science that basically relates the formation and flow to the stress situation that the fluid is in. And most of the rheology actually talks about liquids and soft solids. So you have fluid mechanics that deals with ultimately flow of those fluids. Now in terms of solid mechanics, you actually have similar. You will have stress deformation relationship. It's just that that deformation is really, really minimal and a number of orders of magnitude less than it is for fluids. So when I stress this solid surface, yes, it's actually responding. It's minimally deforming, so I might even discount it as nothing because I'm not that heavy. But depends on the day, I guess. Depends how much lunch I have. Still, it's not large deformation, whereas fluids would simply flow and deform quite a bit in response. The stress itself might actually be the same. It's the response to stress that basically is quantified by this rheological behavior. Okay, so let's actually see some fun. Actually, let me. Apparently, I have to click from here. So let's see some fun fluids.
7 feet long, 3 feet wide, about 2 feet deep. There's 2,500 pounds of cornstarch in here. Is that amazing? Look at that. So now, watch this. You can just punch it, and it becomes a solid at that split second. This is really fun to do at home. All right, so here's the theory.
Some of it isn't solid, you know. It doesn't.
So, okay,
that's
but
weird.
Is that weird? So when you put pressure on it, it doesn't behave like that. So here's what I was thinking. I know you like game shows. So here's my new game show. If you could go from here to here, walking across without sinking, you don't die. All right? So kind of a different kind of game show. So,
And how much have you tested this?
not a lot. We had a little vat of it in the back. And so,
No, seriously, during the commercial he said, we have never tried this before. You just told me you've never tried this before.
Well, that's in a small scale I did, but not like this. Sorry, but in theory, should be great. All right, so
This is crazy because no one has done this before. So are you spotting her? Good.
okay. So when you go across,
You're gonna go fast.
just go fast. Don't stop. All right, and we're gonna catch you at the very end. All right, but go. It's gonna feel weird. Just go across. Ready? Fast. Go. Ready? Go, 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 don't stop, don't stop, don't stop, don't stop. See what I mean? That's it.
Amazing. Brilliant. So we'll be right back after this. Don't go away. One sec.
And you can actually, if you type in cornstarch in YouTube, you will get a lot of these movies. They're kind of popular. So basically, this fluid doesn't react just on the stress itself, but the rate of change as well. So the faster I have impact, there are actually particles inside that will bunch up, and the fluid actually in between those particles will get squeezed out. Okay, so you will actually feel like you're punching a solid. Yet when you don't have a fast impact, it will actually have fluid inside. Fluid will not escape this sort of fluid element. Okay, so it will actually act as fluid. So if you're acting slowly, it's acting as a fluid. If you're acting fast, it's acting. It solidifies upon impact. So that is this transitional behavior in between solid and fluid. And so we need some, of course, different relationship that will that will describe this. And this particular type of fluid is shear thickening, because it's basically with increased shear, you're going to have a thickening behavior. A lot of fluids in industrial or petroleum engineering applications are shear thinning. So foams, for instance, foam is used a lot in enhanced oil recovery. So foam is shear thinning. It's going to flow better as you increase shear stress that you're, for instance, that you're pumping it in with. Okay, so you have different behavior. You have to account for that. Okay. So again, this is just a quick review. If I had actually elastic solid and I was deforming it, my stress or normal stress or other stress is force divided by area, and that force could be normal force or shear force. And then what I'm looking into, if this is actually a normal stress, there is a coefficient, Young's modulus, between stress itself and normalized deformation. So normalized deformation is delta L. So what is the difference in my length before and after deformation and the original length? Okay. So again, these relationships are technically similar. And if you had in shear, you would actually have, you would express tau as a shear stress, and you would have again this normalized strain, so delta L versus the original H, okay, or original width, and basically you would have another, this is a shear modulus here times gamma. Now this modulus is in the order of gigapascals for typical materials like typical rocks, okay. That means that it takes really a lot of, so there's a lot of resistance to deformation, so you will not visibly see a difference unless you really expose it to a lot of stress. So I am, of course, I'm not even close to megapascals. I'm actually standing on something on the order of kilopascals, right? So I cannot deform a piece of rock that easily. We actually have to have much more stress exerted to it. Okay? So this is just a relationship to solid mechanics. And then our fluids they flow under shear stress, so they don't just infinitesimally deform the way solids do. Okay, so one fluid description that is in between the two fluid and sort of solid behavior is so-called Bingham plastic. Okay, and Bingham plastic has an expression between your tau and dvx dy as follows. So this is the same as my Newtonian fluid. It's just that I have actually a so-called yield stress. So I will not start moving until stress is large enough. Okay. So if I expose my fluid to stress that is lower than this yield stress, and think about your the paste for brushing. I missed toothpaste, thank you. I'm missing the word today. Toothpaste, think about toothpaste. It doesn't really flow out of the tube. You have to squeeze it. So by squeezing it, you're applying the stress that is high enough for toothpaste to come out. Ketchup is another. Okay, so ketchup doesn't just flow out of your bowl. So basically, below that value, you actually don't have relationship between shear stress and velocity. You simply don't know what that relationship is. But what's true for your velocity is that it's inertia. It's going to stay what it was just before that or what it is at some point neighboring it. Okay? So if you weren't moving, you're not going to start moving. If you were moving in constant motion or something next to you is moving in constant motion, you will just replicate, like sort of like inertia, just replicate that. So basically, you will not, your velocity will not be different from that point next to you moving. Okay. So that's, I call this inertia part. But the important thing is that actually your shear stress is something that it doesn't affect your movement. Okay. If the shear stress is actually larger than this yield stress, then basically what's going to cause motion sort of in Newtonian way is difference between how much this shear stress is larger than the yield stress. Okay, and that relates, so basically tau ix minus tau 0 relates to what we see as some sort of effective viscosity of this fluid and the difference. So this is, of course, the simplest Newtonian law for our one-dimensional case. We also see that we need two parameters as opposed to one to actually describe this fluid. So let's actually see a little bit of how this works, and I apparently need to go to minute. So there are National Committee for Fluid Mechanics films. They're from 1965, so they're dated. Okay, so have that in mind when watching them, because professors standing in front of you are really stuck up. But in terms of the information or the knowledge, they're really, really great. What impresses me the most is how well they can draw. I rely so much on PowerPoints these days that I don't need to draw well, and they're just drawing like it's a no problem. So we will actually look at where's the rheological behavior of fluids. You can, of course, watch any of them. So I'm actually just going to quickly feed my computer. So I'm just going to...
Rheology, in its broadest sense, is a study of the relationship between force and deformation in continuous media. In this film, we shall focus our attention on fluids.
So this is what I mean by a little... It's 1965, okay? But that said, they're great. And I'm just going to show the part that is related to Bingham fluid.
And this vessel is open to the atmosphere on top, and yet this clay suspension does not flow. I can put this simple piston here, place this small weight on it, still no flow. Now a larger weight. It flows, but very slowly. A much larger weight. The flow is fairly rapid. I take the weight off. The flow stops. In a state of equilibrium, this material can support a shearing stress up to a critical value called a yield value. Even with materials not having yield values, the Newtonian fluid cannot explain many flow phenomena. For many of these, a more general model, that of the memory fluid, does provide an explanation. For the memory fluid, the pressure is isotropic in the equilibrium state, where no changes of either the stress or the deformation are taking place. In relative motion, however, in contrast to the Newtonian fluid, the history of the deformation is significant. Instead of a linear function, the memory fluid reveals nonlinearities. In fact, nonlinearity affects both the shear stresses and the normal stresses.
Okay. So I'm going to stop it here. You can actually watch the entire movie. I just wanted to exemplify the Bingham fluid. You can watch the other. So this is actually a relatively simple relationship. I am actually linear in parts. I just have this yield stress part. So it's a little more complex than just a coefficient times the derivatives. And that already can explain some of this yield stress behavior that we saw. Okay. So again, what makes the fluid a Bingham fluid? We are again in between some sort of solid. There are particles, there are solid particles often within my fluid, and there is some sort of semi-crystal structure, should I say. There's structure to it. So it takes higher stress to actually get that structure in motion, and once I do, I get the motion that is similar to a viscous fluid. But before that, I cannot break that structure and I cannot get to moving, so I'm sort of like a solid before and fluid afterwards. So what we will actually see when we solve the problem, there will be a difference between the Newtonian fluid. So this is actually just half of the tube. So this is R is equal to 0 and R is equal to R. Note that shear stress actually will be similar to the shear stress we have. The slope that is different doesn't really matter. This one is just stretched a little more. So shear stress itself does not change, but how or what is the resulting velocity distribution does. So I'm going to have a parabolic profile up to this. So there's some certain radius where I actually achieve this yield stress. Okay. So above that yield stress value, where my tau is in absolute sense larger than this tau 0, okay? Above that, I have a Newtonian behavior, so I have a parabolic profile, okay? And below that, there's this inertia. I just stay whatever my neighbor is doing. So basically, I just stay at a constant velocity. What I said in the expression is that there is no gradient in my velocity. So this would be dvzdr if I actually had cylindrical coordinates here. Okay. So basically, I will just have no change in velocity in this region where I actually don't have shear stress that is large enough. Shear stress itself, again, is the same as if it was in Newtonian fluid. It's just resulting in a different distribution, velocity distribution. Okay? So we could also have shear thinning and shear thickening fluids. And I'm going to watch one more video. So let me see. I need to go to minute 12:08. So I'm going to go to that.
Outlet. The ratio rates. The basic phenomenon occurring here is more easily seen if the pressure head remains practically constant. These are two identical burettes containing the same Newtonian fluid. The pressure head in one is twice that in the other. The ratio rates of flow is also 2 to 1, as we expect from Poisson's law.
So this is for Newtonian fluid.
But if we charge both burettes with the fluid exhibiting nonlinear behavior and apply the same ratio of pressure heads, the result is quite different. With this polymer solution, when the head is doubled, the rate of flow is more than doubled. It appears that the viscosity is less at the higher velocity gradient. This type of steady flow behavior is called pseudoplastic or shear thinning. There are some fluids that create a contrary situation. For this suspension, the viscosity is higher at the higher rates of flow. This is called dilatant or shear thickening behavior. In the steady laminar flow of incompressible Newtonian fluids through tubes, a single material constant, the coefficient of viscosity, governs the volume rate of flow and the velocity field. Here we get the familiar parabolic velocity profile.
So they put dye in the fluid to actually image this. So you just put.
However, for more general fluids, the flow rate and the velocity field are governed by a viscosity function. For such a fluid, the velocity profile can be very different from parabolic.
This would be Bingham plastic or something even different. But initial profile is like in Bingham. Oh, I love this stuff.
We have seen how nonlinearity affects shear stresses. It also has an unusual effect on the normal stresses. Here is some glycerin, and here is one of my wife's favorite recipes. Why does the cake batter climb the mixing shaft in contrast to the behavior of the Newtonian fluid?
So again, normal, I'm not going to
We can get a better idea of what happened there.
I'm not going to go into details, but you can watch it yourself. So again, you could have simply have nonlinear behavior, and that affects both shear and normal stresses. Okay? So the way we describe that for those are so-called both shear thickening and shear thinning are so-called power law fluids, because the relationship between the shear stress and the velocity gradient is that of a power law. So you will again have two parameters describing it. One will be sort of a generalization of viscosity parameter, and then there will be a power. So if I have n is equal to 1, this will disappear, and I will effectively have a Newtonian fluid. For n less than 1, I will actually have shear thinning fluid, or so-called pseudo-plastic. A lot of foams behave that way, and also our blood. And for n is larger than 1, we will have shear thickening or dilatant fluid, and the cornstarch or sand suspension in water was behaving as a shear thickening fluid. So what makes this fluid a power law fluid? Typically, when I have a Newtonian fluid, I have simple molecules moving around. And our origin of viscosity, we saw that for gases very well, is basically intermolecular collisions. If I actually have polymers in the fluid, polymer chains can get much larger than a single molecule. Okay? So I'll have sizes that are more than 1,000 times larger than my own methane molecule. Okay? So basically, and these chains are nowhere near our little sphere that we were imagining that molecules are. They're actually long. Okay? So in themselves, they actually have rotational moments to them. They don't behave the same way in every direction. Okay? And these polymer chains, they can entangle or detangle depending on the shear stress applied to them. So I will often actually have different behavior depending on these polymer chains, so they could actually stretch out and untangle when I apply the shear stress. And in that case, I'm going to have shear thinning behavior. Okay? Or they could actually tangle some more, depending on what type of chains and what type of course, forces I have between them. So there is attractive forces that could actually try to couple some of them up. And then if they tangle some more, we're actually going to have shear thickening behavior. Foam itself does not necessarily have, well, it has some polymers possibly in the water phase for stability, but foam is actually just a bunch of bubbles. These bubbles could change texture depending on the applied shear stress. So if I have actually larger shear stresses, I might actually have bubbles becoming smaller, making foam effectively a little. Actually, the smaller bubbles, I'm going to have thicker fluid. I'm going to have more viscous fluid. Or they could start merging together. If they start merging together, then we're going to have larger bubbles, and that will actually make for less viscous fluid. So again, foam is bubbles of gas suspended in water. And there are certain agents in that water that are keeping surfactants and sometimes polymers and sometimes even nanoparticles that are keeping those foams stable. Okay? So depending on what I actually have in this game of complex fluids, I might see different behavior. Okay? So in summary, these are all of the behaviors that we have here. So this is my classical Newtonian fluid. This is my, in absolute sense, my shear stress and my absolute value of the derivative velocity. This is again having that one-dimensional Newton law in mind. Okay, and then if I have my Bingham fluid, okay, all I'm going to do is I'm going to just translate this curve to some sort of yield stress values, and only above those yield stress value I'm actually behaving as a Newtonian fluid. Up until that, I don't move the fluid, I don't change any velocity with the shear stress that I have. Then if I look at this shear thinning behavior, okay, so I look at the basically, so the coefficient or the effective viscosity is the slope in this curve, okay? So my slope here is much steeper than it is here, okay? So steeper slope is more thicker fluid, okay? So I'm thinning out as I'm increasing in dVi dx. Whereas if I actually have a shear thickening fluid, then as I increase dV by dx, I'm gonna have a steeper slope and effectively larger viscosity. Okay, so my effective viscosity that I measure on the outside, if I just assume that this is a Newtonian fluid, will appear much larger than it is at lower dVi dx. So that is shear thickening fluid. Okay. So it could also get more complex. I could have so-called time-dependent fluids. In essence, I could have what was also referred to as a memory fluid. So it might be actually very much dependent on how I get there. So for instance, if I had one of those polymers that detangle, maybe I can't tangle it up again. Okay? So it's not that I just change the speed at which velocity is moving or the gradients of change in velocity, and then everything changes back up. So it might actually become a different fluid once I actually go through the process once. So I'm history dependent. Okay? So that is the time dependent behavior. So I can't just go up and down and change things the way I want. So I might have time dependent behavior. So what I might actually stop changing my shear stress, but I still see change in viscosity because my fluid relaxes after a certain time and so forth. So there's a lot of complex behaviors that I could actually have bundled up. In most of these fluids, in most complex situations, I might still look at what we call effective viscosity. So even though I know the fluid is non-Newtonian, I'm going to measure viscosity as if it was. Okay, so I'm going to fit it to that relationship. Tau yx is minus mu dvi dx, or if I have a different geometry, maybe it's going to be slightly different. So in that sense, I can assume that relationship and fit the values and still find effective viscosity. Similar is done in petrophysics. You're going to look at effective permeability of a rock, regardless of whether you actually have a simple relationship and whether your Darcy's law is actually applicable. You can still look at effective permeability because those are the simple things you can measure from the outside. So basically, if I just measure from the outside, I can still get an effective viscosity value. So for any extra reading on these complex fluids, you can go to chapter 8. Okay. So, okay, we will move on to we will do compressible fluids when we are actually when we are ready to solve for them. Well, I have 5 minutes left, so I will at least introduce a problem so that next time we can actually start solving it. So we will look at the Bingham plastic. So our example is Bingham plastic or fluid. It's often called a Bingham plastic in a horizontal tube. Okay. So again, I have horizontal tube, so I will ignore gravity, and that is tube of radius r. So this is my z direction, and this is my r direction. The actual, well, technically speaking, I'm starting in the center of the tube. I'm starting my coordinate system. And what we said is now I'm going to look and express things as tau rz in absolute sense. And here my only non-zero velocity will be vz. So we will assume again vz of r. And any other, since I don't have gradients driving the flow in r and theta direction, they will be 0. So here my shear rate will be dvz dr. So that's what we actually refer to as shear rate. And often will be called gamma in literature as well. Sometimes gamma. So what we'll have here is that instead of starting at 0, it starts at some tau 0. So this is my Bingham, and Newtonian fluid would be here. Now our general form, okay, will be the same as before. So if you remember, what we derived for a tube, a vertical tube, was partial phi zz partial z minus 1 over r phi rz plus rho g. And I'm actually going to just ignore this part. Okay, so I'm gonna remove it. So this is my general flux or z momentum balance ignoring gravity. So this part is still valid. And actually a lot of the derivation, so this part is valid, and we know that my phi zz is pressure plus tau zz plus rho vz squared. And my phi rz is tau rz plus rho vz vr. And vr still being 0, this will be 0. So this is tau rz.
Is the tube in motion? Or
This is for tube.
moving? Is the tube moving?
Is tube moving?
Yeah, like is it stationary or is it in motion?
No, tube is stationary.
What is the driving force for?
A difference in pressure. So just like before, we will actually, when we plug this in, we will get, I will not derive it again, 1 over r d dr, r tau rz is equal to minus dp dz. And just give me 1 second. So just like before, without saying what tau rz is, I can still solve for it. So it's going to be minus dp dz r over 2 plus c1 divided by r. So this was same as before. Oh, so what will differ is now when I actually want to get velocity distribution, I will actually have to look into case where tau rz is larger than tau 0 In the case where it's not, then figure out where that actually is. Okay? And that we will continue next time. So this part so far is the same as if we were solving for Newtonian fluids. All right, we will finish this next time.